can talk a little bit here. I think you're seeing a screen share first of the page that's about my book that is a splash page. And if that's just a gnosis.cx, that's my domain, and then /cleaning, and it's relatively memorable. And there's information on the book, like the fact that I'm talking to you right now and highlighted, and stuff about buying it, but also you can get to most of the content in the navigation. So today I'm going to talk about anomalies, which is one of the chapters. If you go to the web page, it's all broken down into little bits, so you can click on the little bits to read. A few of them, because my publisher is foolish, are blocked out. Like if you click on exercise, it'll just say buy the book, and it's very silly, and I don't want to do that. I just want all content to be free always, and all software to be free always, but sometimes I have to navigate with things like publishers. Nonetheless, just to let everybody know, the main stuff I'm going to be talking about today is from the Jupyter notebooks I used in writing the book. And if anybody wants those, just send me a private email and I'll make that happen. I want this stuff to be free, so just don't CC Pact when you do that. But let me talk a little bit kind of about what I do overall in this project. I mean, I found that in my work as a data scientist or data engineer or software developer in a variety of ways, I deal with a lot of different data that comes from a lot of different sources. And it's always this, not really a secret, but it's always sort of de-emphasized the fact that when we do things like machine learning tasks or data visualization tasks or statistical analyses of whatever our particular purpose is, there's this huge part. In the title of the book and so on, I use the figure 80%, but you can, pick slightly different numbers. But the point is that it's like this large majority where you do a lot of work in making your data in good condition, and then you do something like, put it into your sexy TensorFlow model or your whatever, or your, very interesting, interactive, faceted data visualization. But this large part of what your work is going to be as something like a data scientist, data engineer, is sort of minimally spoken of. And you can get a variety of books on this interesting new library, that the machine learning library or visualization library, and they all have sort of this throwaway preface or part of a chapter or something like that discuss, well, you really have to spend a lot of work cleaning up your data before you can do any of these other things. So I decided that I wanted to write the book that is the throwaway preface to every other book that is in this general domain. So I think I've done that. I think I've done a nice job. And I believe on screen you're seeing, let's even change the view here to the simple one so you see even a little bit more of it. You can kind of see the things that are available in this book. And obviously I'm promoting it, so if you want to buy it, but if you can email me, you can have all the content too. But I talk about things like ingestion of different kinds of formats where there's kind of characteristic problems that occur in particular formats. And there's some differences. I mean, something about the actual representational form of the data makes certain kinds of problems more likely. So there's some discussion of things like CSVs and databases and like scientific formats like HDF5, and some general discussion of data frames, which is maybe kind of thrown in there, but it's an important technological approach to working with data. And I talk about things like hierarchical formats like JSON and XML, and those, again, have some special issues. And some things like data acquisition that has other forms that don't quite fit into those other categories, where maybe you need to get your data through web scraping, which is kind of awkward and definitely not the way you most want to get it, but sometimes that's the reality. or similarly through PDFs that might have data content and you want to figure out how to extract that. And there's a variety of techniques and of course a variety of characteristic problems that come with that, and a few others, things like oddball text formats that they're textual, so there's not binary data to read, but nonetheless they're, where they put data inside of it might vary, and you deal with that. Then I talk about what I'm going to talk about a bit more detail today is anomaly detection. You've dealt with whatever particular data format that you need to process. And for some particular project, of course, it may be multiple such formats that each has their characteristic issues and you've unified the data in some way. But it sort of goes in cycles. There's kind of three movements to this overall steps that one does as a data scientist and that I more or less follow in the structure of the book, where there's a question of getting the data, ingesting it, dealing with the actual formats that it arrives in. Then there's the question of analyzing what is kind of more structurally wrong with it. Where are there problems that are inside of the data conceived abstractly rather than in the particular representation? And there's a couple of different ways to look at it. In one hand, there's looking at the kind of individual problems. One particular observation of one particular variable is not believable for whatever reason. It's statistically uncharacteristic, or it's simply a missing data value, or it's in some way coding something that you don't think is likely to be a true observation. And of course, the cause of that can vary in a variety of ways. Maybe you have unreliable instruments, or maybe human coding was involved, people at keyboards and maybe they mistyped things. There may be transcription that happened at various points where things were transferred from one kind of representation, one database or one kind of flat file or one particular kind of data to another, and something about that transcription process introduced certain kinds of errors. And so this, what I'm going to spend the bulk of today's talk about, I'm going to look at that, these sort of individual problems that can arise. So I'll come back to that in more detail, but there's sort of several respects in which you can think about that. But then once you've thought about that in your journey over completing one particular project, there's also more systematic problems that can arise in data where there are patterns in the distribution of data that don't feel like they're plausible, or there's bias introduced into the data, both in the sort of human sense. If you're making observations about people, especially, often things like social bias can come in, but it's not always that. Sometimes there's bias in the sense of, you have a measurement from a spectrometer, which is, not a human bias kind of thing, and yet it has a greater sensitivity in one particular spectral region than another. So it introduces a kind of bias there where certain kind of data are overrepresented or underrepresented based on, things about the nature of instruments or things about the structure of observation. So those are important to look at. And those are often contained in the data sets that we want to think about. And so not in what I'm going to be talking in great detail today, but in the stuff I've written, I talk more about a variety of aspects of that and how to approach those and how to identify them. And then there's kind of a third movement of what you want to do in your overall project. You've identified these problems, whether they're problems with particular individual data points that are unreliable in some way, or whether they're problems that pertain to kind of the structure of your data overall, the relationship of the entire aggregation of it that may have bias or other kind of issues. But at this point, before you move forward with it, you want to remediate that in some way. And the remediation in turn has sort of the same kind of division as the analysis of the problems. On the one hand, maybe there are these particular data cells, these particular observations that you either didn't collect in the first place, so they're missing data, or you decided through your analyses are not trustworthy data, and so you've made them missing. You've assigned missing values to them or marked them in some other way to do that. But you'd like, for a variety of purposes, to impute values to those things that are either initially missing in the raw data or made missing by your analyses, so that in some way something reasonable or typical or representative is contained in those data values, because your pretty visualization or your machine learning model or your statistical technique needs to have something there. It doesn't know how to deal with just an absence of data at that point. Even something as simple as taking a standard deviation of a series of data or something like that. You need to have data for all the observations. And so imputation can come in to make up values that are plausible for those particular things. Of course, with a very careful attention to versioning and recording the fact that you're doing imputation, because you don't want to have artifacts emerge purely from your imputation assumptions or your processes. But nonetheless, you're versioning your data and you're imputing values in particular individual points where you think that there's something unreliable, and then your visualizations, your models, whatever, work better as a result of that. But then in turn, there's sort of one final bit of the cycle where you actually want to look at your data again systematically, not in terms of the individual data points. And in some sense, you want to impute, but what you want to impute isn't individual values, but entire kinds of observations that you weren't able to make. That is, synthetic features, things that in some way are already the abstraction of one or more features that you could directly observe, to create new features, synthetic features that are derived from those things that you could directly observe. And those in turn, likewise, may be valuable for your visualization, your modeling, your statistics. And so it's a kind of imputation, but it's more like a column-wise imputation than it is a data cell-wise imputation. And of course, that's important to do as well. And after you've done all those steps, that's the 80% of the work that gets you ready to do the next stuff. At that point, you have this relatively clean data, and you're ready to use some nice machine learning model and make predictions about whatever your particular domain in your problem is. And please interrupt me and ask questions and chat, or just on voice. Actually, let's see if anybody said something relevant in chat, just some introductions so far. But I want to go into maybe a little more detail about some of the particular examples. In this particular anomaly detection chapter and topic, I have a fairly long discussion about missing data and how that tends to be marked in different formats, and where sentinels are used, which is kind of an interesting thing. I'm sure that people have encountered data that there's, say, a particular column of data. It is a numeric column, but sometimes there's no observation available. So they'll often use a sentinel value to represent that. And very often you'll see something like a 999.9, where you have a series of nines that's sort of visually distinct, and that's the representation of missingness, but it's a number. So it's sort of confusing, because why is that clear? That's not actually an observation. And ideally, when you do that sort of thing at the recording step, it's clear because it's dramatically outside the range of plausible values. So you have, for example, values that are, from 0 to 10 in reasonable measurements, and then you record 999. okay, probably that's not a real observation. It's one of these sentinels that's holding the place. Um, but you do definitely have to clean that up, because that 999, if you do any kind of statistics on it, is going to throw everything way off. And so that's a problem. Or sometimes if it's a kind of format that has a string representation of the missingness, there's a variety of different ways it can be spelled. It can be spelled N/A, or it can be spelled as the word missing, or it can sometimes be more specified, like you have observations of people where you get their names, and some people have middle names and some people don't have middle names, but some people simply don't provide that when they fill out the form. So there's this distinction between somebody really doesn't have a middle name versus they've decided not to indicate it on the form. Um, and those are missing, but they're kind of missing in different ways. And maybe in your data, they're going to be marked with different sentinels, and maybe you want to handle them differently on that basis. So there's actually quite a bit interesting that's going on with missingness and sentinels. But I think for today, I want to talk a little bit more about a couple other things. I mean, you can look at this stuff on the website, or if you want to get the book or whatever. But let me talk in more detail about miscoded data, and then a little bit about outliers and how you look at those. I imagine a lot of people have done a lot of this, so this is probably not entirely new, but nonetheless, maybe I'll have some interesting things to say about it. So there's a data set I'm looking at here. This is a publicly available data set that was dermatology data. And this is in the UCI, University of California at Irvine, machine learning repository, which is a fairly well-known site that accumulates data sets that are nice examples in machine learning. And this particular set, it's not particularly large, but it has these patients that we're trying to diagnose some particular skin condition. And they were rated on a variety of observable characteristics, and then with the goal of ultimately identifying some particular named skin condition that would be presumably treated in some particular way. So it's a nice little example data set. But in particular, if you read the documentation on it, you see that there's this ordinal encoding of most of the characteristics. So here I'm just importing in the repository for the book and so on, you can import a couple objects that I just put together, whether they're functions or whether they're data sets or something. So one of those is this dermatology one. So we can take a look here at the just making it into a data frame and so on, massaging the format that UCI gives you, and take a look at the various features and what values were given to those. Well, in the metadata that describes it, it says that each of these conditions, like erythema and scaling and definite borders and so on, are something that may potentially be observed, and it will be given a 0 if there was no degree of that observation, and then numbers 1 through 3 if it was, to varying severity of that particular thing. And there's a bunch of those. There's 35 total, so 34 observed features. And then there's one particular diagnosis, which I'm calling target, and you can see that there's a couple examples like chronic dermatitis and seborrheic dermatitis, which are the final diagnosis which the patients might have. And I want to look at this data set. And it's interesting, this is a well-studied, widely used data set. And I still think there's going to be data integrity problems in it. There's data cleaning that needs to be done, even in the most analyzed, the most used, the data that has many, many passes that have been made over it. But in particular, I could just use a little description here. And I find that for most of these features, there's a minimum and a maximum, and indeed they go from the number 0 to 3. So that feels fairly happy there in terms of the data quality kind of thing. I do notice that there's a particular data field called age, which goes from 0 to 75, which is reasonable enough. Those are human ages, and those could be the patients. And I think I actually go off in a different direction here, which maybe is a little bit of, we're going to return to the dermatology one. Let's look again at this little data set that I have. This is an example that I've used in teaching. It's partially real and partially made up by me. That is, that I've actually got some data on distribution of typical heights and weights of people. And so some of this is based on at least statistical characteristics that are known observations, probably in the United States. Perhaps these numbers would be slightly different elsewhere. But we have people have a variety of heights and a variety of corresponding weights. And I've made up this figure about hair length, where, their hair is of different lengths. And to make a categorical field, I've made up a favorite color for different people. So this is sort of phony data, but it hopefully has some characteristics that are realistic. And when I start to look at this, I want to do a few things to analyze it for anomalies in particular, like look at these unique values. So we see that these favorite colors have, I'm expecting it to be categorical. It's should have some finite number of unique values. And we see that there's a collection here using the pandas as a way of looking at that, where we see these variety of names of different colors. And obviously a couple of them look a little bit funny. We can see that a little bit better when we do the value counts, which is a good next choice. Whether you're doing this in Python and pandas or using some other tool, there's going to be something available like this, analysis, a histogram basically of the frequency of different categories. And I see here that in my hypothetical data, I have a lot of people whose favorite color is red and a lot whose favorite is blue, and likewise for green. And so these all seem fairly unproblematic values. But I noticed that one person has the favorite color chartreuse, which is a perfectly good color name. It's a kind of less commonly used word than those others. So I already sort of have this question about what am I going to do with that particular observation? Do I think that that's an anomaly, that someone has this very unusual favorite color choice? Or is it just that it's uncommon to have that particular favorite color? And that's the kind of issue that I want to pose to myself when I'm doing this, data processing step. Obviously, this is a bit artificial in this particular example, but this is an issue. And at this point, besides other issues, I might want to go back and think about how the data was collected, if I have access to that information, or if there's metadata associated with this data set. Like if somebody filled out a form and the only bubbles were red, blue, and green, then, how did chartreuse get into the data? It was perhaps not something that could be collected in the direct way. The fact it's unusual doesn't prove it's wrong, but it does immediately raise a certain suspicion in my mind of being an anomaly. And then I see a couple other things. I see green that looks just like the above one, but it's somehow different. And there's just one of those. So something funny is going on with that particular category. And I see a couple others. Red with the extra space before it, red in capitals or, initial capital rather than in lowercase, like most of the names seem to be. And this, blue with a gratuitous umlaut in it. And all of those immediately jump out to me like these are anomalous values. The thing with the extra space at the beginning is very much, looks to me like it's probably a human transcription problem. I'm almost sure that someone meant to just type red, but they hit the space bar accidentally. So that I feel like I know how to handle that, but I do need to identify that. It's not, I have to use my human eyes and make a certain kind of judgment about that value being not typical or anomalous. And the one with the funny U with the umlaut over it, kind of the same thing. I mean, maybe they're using a German keyboard when they're doing the entry and it has the umlaut character on it more directly. But what's the same about all these cases that are merely unusual is, in the first case, just that they are rare occurrences. But the fact they're rare in themselves doesn't give a single path to how I'm going to deal with them. I mean, so in a sense, they're anomalies, but perhaps they're anomalies just because of the distribution of the underlying phenomenon, and only a very few people have a favorite color of chartreuse, or that perhaps they're anomalies because people make keyboard entry errors. And these are different kinds of cases that we probably want to handle differently. Well, there's a couple that are just a bit mysterious. Like, why did I see green that looks just like green here? Clearly, those are different strings, even though they look like the same string to me. Maybe it was a trailing space, and the trailing space is not appearing in this notebook here directly. But let's actually look at the particular bytes that make up those various strings that describe the categoricals. And what we see here is, well, capital red is not particularly mysterious. It is a little mysterious. What is the 32 at the beginning here? Oh, that's the first one's the one with the space at the beginning, which is the 32 character, and 82. But then the 101, 100, that's fine. This is fairly straightforward. There's a couple different ways of mistyping red, and there's a way of mistyping blue that has one character out of place. The green is a bit more mysterious. This looks like one of these phishing attempts. What it in fact is this here is a Unicode representation of the Cyrillic letter Ye, which looks just like the letter E in Roman alphabet. I mean, I feel like when I see that, it's probably a case of malice, like when people do domain name phishing, where they substitute something that looks almost the same to try to get you to, go to what you think is your bank or something. But in any case, it's the wrong character, and actually digging down into the actual bytes that make up the particular strings may be necessary to something along those lines. You have to inspect what's really going on there, not necessarily just how it visually looks to you on screen. Anyway, so what we might typically do here in this remediation is we have some things that are anomalies. That we find that the oddball spellings of red, either with the extra capital or the space, I'm just assuming, as the domain expert in this particular data set, that what was really intended was that these were intended to spell the word red in all lowercase with no spaces, and just someone made a mistake in how it was transcribed. And so I'm just going to impute the value of what I think is the correct canonical spelling. Here, we'll go ahead and view line numbers to talk about it. On the line 1, because I feel like I know enough about the data that I feel that's a reasonable thing to do. Misspellings of red mean red. Now misspellings, not misspellings, but the value chartreuse is questionable. It is a correctly spelled word for an actual color name that's not used so commonly. What do I want to do with that? In this particular case, I've decided that I'm going to make that a missing value by explicitly calling it none, under the assumption, and this is not universal, it's not enough to say it's unusual and therefore it has to be missing, but as a domain area judgment or a task-driven judgment, I've decided that my later processing isn't going to be able to deal with this very unusual value. So I've made the deliberate decision as a data engineer or as a data scientist to assign that as a missing value. Of course, I want to keep the original. I don't want to throw it away forever so I can never get it back. But for my hypothetical downstream processes, that's the way I want to treat it. And then the funny things with the umlaut in the blue and the Cyrillic character in the green, I'm just going to do much like I do with the red. I'm going to canonicalize the spelling to what I believe should be the correct spelling. And then after this kind of cleanup, I have just 3 favorite colors that I'm actually using, and they're, all commonplace. So this is one, this isn't a guide to how to do this kind of thing always, but these are kind of the problems and categorical values that you tend to encounter, and you have to make these kind of decisions about the correct processing of them. I'll go very quickly through it, but I want to contrast here the notion of fixed bounds in your data versus derived bounds, or derived statistical anomalies that are outside your expected distribution, because this is another aspect. We've moved from the categorical data to looking at numeric data. I'm not sure why I introduced the dermatology thing I did earlier. I do deal with it later, but it probably should have gone somewhere else in the book where I imported that. But in any case, we have these humans that have various heights. And we find that in our particular set, which is not tiny, it's, I think, 25,000 hypothetical people that are in it, none of them are below 92 centimeters and none of them are above 213 centimeters. And I took those numbers, oh no, those are not, those are, I forget exactly why I chose those numbers. I do have a little note about the tallest human ever was this particular Robert Pershing Wadlow, who was 271 centimeters, and the shortest adult human was Chandra Badr Dangi at 55 centimeters. So those are definitely outliers, but those are not incorrect observations. Those are very rare, very, very tall and very, very short people, but they were actual humans that I think they're both have died now, but they were at some point actual living humans that had those very, very unusual heights. Nonetheless, in data that we observe, we're very unlikely to come across those particular, world record tallest and shortest people. So it might make sense to impose, or at least check for, a more limited bound where we think that it's very unlikely in sort of the real world, or in terms of what our tools or later processes know how to deal with, to encounter human heights that are outside of that range of 92 to 213 centimeters. And in particular, we find out that indeed, none of our data has that problem. So we have a certain reassurance here in cells 23. We have this other one. Some people have obviously different lengths of hair, and I'll probably not get to it just because I don't want to talk for too long today. But we might think that having a hair length, likewise, of more than this 120 centimeters would be sort of unrealistically large. Or we might even think that we know something about the collection process of the measurements that were made on hair, that there was actually a measuring tape that was 120 centimeters that's supposed to be used by the surveyors. And so therefore any measurement that's more than that, couldn't have been made with what we believe to be the instruments that were used. It's very easy to imagine an actual measuring tape that's that length, and that, may be the equipment. If so, we know that any measurement past that is probably some kind of error. Like perhaps it's a transcription error, and all these people who supposedly had 127 centimeter long hair actually had 20 centimeter or 27, like the one was, a typo at the beginning, or some other kind of typo could come in there. So it's 25,000 rows. This is a pretty small number of them where I have this possible problem going on in this anomaly. But I do think that these are anomalies. I think these aren't the right measurements based on my stipulated domain knowledge of the kind of tool that was used to make the measurement. And therefore, something has gone wrong with the data, and we have to make a decision about what to do. Maybe we just want to discard these rows because there aren't really that many of them compared to the overall data set, and we could just get something cleaner where we drop the ones that are problematic. Or maybe we want to make some kind of imputation, which isn't really this chapter, but it's the thing that should be in your mind, where maybe we want, for these measurements we think are unreliable because they exceed this bound that we think the instrument was able to provide us, perhaps we just want to assign a mean or a median or some kind of typical value for those measurements, but keep the rest of the data because we feel like the other measurements that were made are probably correct, probably relatively reliable. And so we don't want to just discard rows willy-nilly. But that's a decision we need to make that is really driven by our task purpose here. But we might drill into this. And here, notice that I'm versioning data. This is a sort of good example of, I don't want to throw away the measurements, that the rows that are potentially problematic. I want to keep them around so I can return to them. In this case, because it's relatively small, it fits in memory, I'm just going to make copies of the data frames as I go along, and every earlier one has a name. But that, if you're dealing with large data, you're not going to do it that way. You're going to, simply put in code content, comments, and, annotation in the overall documentation for your project about the kind of transformations you made, but keep the very original one and then do these various modifications to assign things that you think are more likely. Yeah, let me try to wrap this up. So, and I'm finding, so here's a possibility. I could say, well, all those people who apparently have these hair lengths of over 120, I'm just going to give them the value 120. And then you can see that I've clipped them, as I say. I've made the threshold for what I'm displaying slightly smaller, but you can see that there's a small number of numbers that are exactly 120, the maximum I think that my instrument can observe, and there's a few that are kind of clustered just very slightly below that. Probably in 25,000 rows, that's not going to throw anything off extremely, but I'm making a judgment about that. But then maybe I want to probe into this even a little bit more. And I find that these humans, that quite a few of them, I mean, not the majority or anything, but 517 out of the 25,000 have 0 length hair, which is, I mean, I haven't shaved for a while, but it's a plausible length. Some people are bald. That's either because they shave their head or they, are just bald. So this seems pretty plausible, the zeros. I'm not really worried about that. That makes sense in the distribution, and it makes sense relative to the stipulated instrumentation I have for observing the lengths. On the other hand, I know in the domain that having a negative hair length is really nonsensical. And so I can be pretty sure that if I do this filter here, just using a pandas technique of looking for the negative numbers in hair length, and there's 118 such purported observations, something bad is going on with those. Those are definitely not real measurements. So again, I have to make the decision. Am I throwing out that data because I just find those rows unreliable? I think they're corrupted in some way. Am I going to impute a mean value for those? Am I going to do like I did before, where I would clip them at 0 exactly if it was a negative number, like I did with the very long ones? There's different approaches I could take. And it's probably not enough data that it's probably going to make a big difference for most purposes. But let's suppose it was more. Let's suppose it's a significant fraction, or I really, really care about those particular 118 rows. How am I going to take a look more closely at what's going on with those? Well, I could get some statistics on those. Here I could do it in R, and I do the same thing in Python just to sort of show that different tools are roughly equivalent in this regard. And I find of those, it's not necessarily immediately informative that I have a certain mean supposedly negative length and a certain standard deviation, and maybe something's going to jump out about that. But where it jumps out more in my mind is if I actually look at the distribution of these supposedly negative lengths. So I'm doing this visualization and I find that I don't think I haven't shown it yet, but basically the distribution of positive hair lengths is sort of a similar curve. There's a lot more data in it, but it, has a lot of people close to zero, and then it trails off in a, exactly what the algebraic form is, I'm not sure, but it is in a decaying way where, the long lengths are increasingly less common. And the negative length looks similar in the distribution, at least to my eyeballs, to what the positive length looked like, which gives me a certain suspicion that maybe what's happened in the data corruption is simply a sign inversion somehow in what was recorded. I mean, if we flipped the sign on all of these, they would be kind of reasonable values, and they would follow roughly the distribution that we expect of the positive values. So maybe what's going on is this sign inversion in the in the data collection or the transcription process. It's a working hypothesis when I'm trying to clean up this data. But I'm going to probe even deeper into this hypothesis. Obviously, this is whimsical data, and it's probably not the data you're really going to be dealing with. But if it were, and you really want to save the data as much as you possibly can, you could ask this additional question. The picture itself looks like sort of the inverted distribution I would expect. Let's look at the value counts in particular. And what we notice here is a whole lot of -1 exactly. Even if I displayed more decimal points, it would still be exactly -1 there. And a variety of other values. A couple of them occur 2 times, but in general, most of them just, some precise value occurs once. So I feel like the sign inversion hypothesis is going to make sense for the overall distribution, but it shouldn't produce that many that are exactly -1. And then at that point, I recall that -1 is one of the numbers that's very commonly used as a sentinel value in data. I mentioned earlier talking today that this value like 999.9 was something that was often used as a sentinel value to indicate that a measurement wasn't available. But -1 is another one of those very commonly used, especially for things that generally should be positive, to indicate that you weren't able to make an observation, or someone upstream from you who made these, recording of the data, they'll often use that value. So my feeling is that the -1s are more likely to be these sentinel markers. No observation was made for whatever reason, while the others are likely to reflect a sign inversion of the data. So that's quite a bit of forensics, and it's quite a bit of forensics for a fairly small amount of the data in this case, but it's the kind of thought process that I would often go through in, trying to figure out what's gone wrong in this data that, simply arrived at my desk that I need to do this other process with. And I think that's probably about the time I should be going. Here it's just a little bit of stuff where I kind of do exactly what I said. I say, if it is exactly -1, I'm going to assign it as missing. I believe that's a sentinel. If it was a different negative value, I'm going to think that a sign inversion was made. And again, just to emphasize, this is not the only possible approach to this. This is a way that I might think through a particular problem. But indeed, we produce this nice distribution, in this case, under those particular assumptions that I decided to make for this particular data set. And that kind of process thinking, I think, is very typical for many kinds of data sets. And I would love to talk about more, but I'm sort of out of the time. But in the next bits, I talk about outliers that aren't defined by fixed boundaries. Like I know 120 is too much, I know 0 is too little, but rather you look at the distribution of the data you actually have, and you look at what's sufficiently atypical statistically that it's likely to be an outlier. And there's a couple techniques, like one's called z-score, which is just basically just the number of standard deviations out, that can be used to detect things that are like that. And another one is called interquartile range, where you look at the quartiles and how much is distributed between quartile 1 and quartile 4, and a multiplier of that, and so on, that is similar in terms of identifying things which are not a priori fixed bounds in terms of what you think are reasonable values, but based on the distribution you actually encounter, they're very unlikely to fall within that distribution of the rest of the data. But it's a very similar kind of concept to what we did with the fixed bounds. And so in the interest of time, I'll stop here, but encourage you to read the material in writing later.
Okay, thanks. Thanks, Dave. That was very interesting.